Hello again, everybody. Welcome back. So I invite you all to join us now for this session, which will be the second in our technical workshop series. This session will focus on EASI gold standard. So it offers you a chance to be able to understand what the potential is, what can really be achieved when we use Earth observation data and science for climate change related projects. I'd now like to hand over to our colleagues at CSIRO to be able to do this presentation with us and work you through this session. So over to you, Eric. Thank you.
Thanks very much, Roshni. Hi, everyone. Thank you for attending this session. It's great to see so many of you here. Gold standard. I'm not 100% sure exactly how that title came to be for this particular session. Let me just say, okay, what we're going to look at in this session is look at a notebook that I put together as part of this project. But let me just start by saying that there are a vast variety of notebooks available for all of you out there. Notebooks that you can download and you can install on your own system or on the EASI platform, and that you can use as a stepping stone, if you like, to develop your own application and your own ideas. Different databases of notebooks that come to my mind are Digital Earth Australia, DEA notebooks, DE Africa notebooks, and there are many, many more. And all these notebooks are gold standard in the sense that they all have very, very good information in them, very good way to describe what's happening and to explain how to do the kind of things that you might be interested in. So just get out there, have a look around, and you will find many of these gold standard notebooks ready for you to use. So what I'll be doing over the next few minutes, half an hour or so, is to go through one of the notebooks that I've put together. And every time I write a notebook for a project or an application, I try to use kind of best practice approaches or best practice approach to try and come up with a product that I can share with other people and that provide as accurate an implementation as possible, as relevant as possible. So hopefully this is kind of a message that will that you can take home going through this notebook this afternoon. So let me just share my screen here. Hopefully you will be able to see my notebook shared with all of you. And please, someone let me know if that's not the case. So this notebook is, as you can see, about measuring sediments in Lake Tempe. Thanks, Roshni. And it provides a bit of a typical way of how I would implement things in a notebook such as this one. This notebook was derived in a project that I contributed to with staff and collaborators from Hasanuddin University in Indonesia, and they were quite interested in trying to find a way to measure sediments, suspended solids in Lake Tempe at the time on the basis of remote sensing data. So in this notebook, I'll step through various parts of the processing and hopefully demonstrate the basic kind of steps in the workflow that I typically use in my applications. So we'll be touching on a number of technical and computational aspects in this notebook. I won't go into the detail of the code per se, so I won't spend too much time trying to explain to you what the code is doing. Later on this afternoon, there's a session about tips and tricks of using the EASI platform, and one of my colleagues, one of the other organizers of this hackathon, will go through the detail, through some of these steps in a bit more detail with you. So I'll keep this presentation here as a bit of a high level overview of a typical workflow, what's feasible with a typical notebook and this kind of environment on the EASI platform. So as you can see here, I've logged on to the EASI platform online, and I'm going to run through each of the cells, each of the code blocks in this notebook in real time. So fortunately for this application here, the data set I'll be looking at is fairly small, fairly restricted in space and time. It allows me to do the processing in real time with you. Okay, so let's get started. As some of you might know, the notebook I find this to be a fantastic tool to do your coding, to do your implementation and your documentation of the code. So as you will see, as I scroll through this notebook, there is different cells and different ways that you can use this tool, including doing sections and writing text and writing equations and doing your codes, as well as providing the results from your code. So that's one of the fantastic aspects of the Jupyter Lab environment. One of the less attractive aspects of this environment is the fact that it's a bit like viewing a web page, in that you're scrolling through the notebook, and for the audience, it's not that great because there's a lot of material that will scroll past your screen and that you might not necessarily have the time to view yourself or to read. So I'll make a point of stopping at various parts in the notebook so that you can take a bit more time to take in what's happening and to look at the results. That being said, this notebook here will be part of a suite of notebooks that will be available on the EASI platform, and that you can download yourself, that you can install on your own personal space on EASI, and you will be able to go through the same steps of this notebook at your leisure later on. So here is the background. What I'll be doing in this notebook, or what this is all about, is contained in this set of equations here, which I've highlighted in the middle of the screen. So the people I did this work with at the time were very interested in calculating an estimate of TSS, which is total suspended solids in Lake Tempe on the basis of remote sensing imagery. And so we looked a bit around. We looked around for a typical example of how to do this, and we came across this publication here, which you can download and have a look at, in which they present this set of equations here to calculate an estimate of suspended sediments, TSS. And so at the time that they put together their paper, the authors went on the lake, did sampling of lake waters at various points in the lake, and they kind of correlated this with a satellite overpass, so a measurement taken from a satellite at the same time from Sentinel-2 dataset, from the Sentinel-2 sensor. And then they created this relationship here in the center of the screen. They fitted the relationship to be able to then apply the relationship, the algorithm, to the rest of the imagery. So this is exactly what we'll be doing here. We'll be loading up some data from Sentinel-2, and we'll apply this set of algorithm, this set of equations here, to the data to be able to come up with maps of TSS, of estimated suspended solids, for the whole of Lake Tempe through time. And then on the basis of this, we can derive other parameters of interest, statistical summaries, averages over various periods of time, anything that might be useful for the person who is carrying the work. So we'll start with executing a couple of cells to get the notebook started. And so what you will get a bit more of an idea about how to run notebooks a bit later on today in the tips and tricks session. But basically all I'm doing here is scrolling through each of these cells and then executing it as I go. And as I execute it, you will actually take the code that's written in the cell and execute that. So I've executed the first cell and the second one here. As you will see, the others will have a star in it while it's processing, but quickly get to a number once it's executed. So the analysis window, the analysis parameters that I'm looking at are given here. So the longitude and latitude extents are given in this code cell up here, and this display map function here can be used to have a look at the area of interest that I'm processing in this notebook. So this gives you an idea of where Lake Tempe is located in Indonesia. You can scroll around and play around with this later on if you're interested as well. Now, for the current example, I'll be using 3 years worth of Sentinel-2 data. The Sentinel-2 time series extend for longer than that, but in order to keep things tractable in this notebook, I'll be using 3 years from 2018 all the way to the end of 2020. So I define my dates this way. The next section is about loading the data. I'm loading a product called, well, with this label here, which is a Sentinel-2 product. So I just define the parameters here. I define a query to be able to integrate the data cube, and you will see sometimes you get some warning messages, which in this example actually don't reproduce once you re-execute the cell. So sometimes there's warnings that you don't have to worry too much about. If the code crashes and stops working, then you will know that it's something that you have to fix. But in this case, I'm not too worried about these warnings. And now I look at the measurements available for this satellite sensor. Sentinel-2 has all these bands here available, but I will select only a series of measurements that I use for, or that I require for this algorithm that I was talking about. So I built my query, which will look like this. So I've defined the product, the latitude, the longitude, and the time of my query, as well as the bands that I'm after here, as per the algorithm that I talked about earlier. And this is where the data set is being loaded. So this takes a bit of time because it's this dc.load function here interrogates the data cube and then loads up all the data in my JupyterLab environment. So it will take a couple of minutes. As I said, I'm only using 3 years worth of data, so that allows me to do this on the go. This will still give me, still take about a minute and a bit, not 2 minutes. So in the meantime, I will open a terminal and move the window to the side. And I just want to fire up a little command here that allows me to see what's happening in the JupyterLab environment. As you can see from this kind of display here, I've got 8 CPUs, 8 processing units available to this notebook, and a total of about 30 gigabytes worth of RAM, of memory. So this is something that I like to keep on the side because it shows me what each of the CPUs are doing. And we can see that one of them is being used. It switches from one CPU to the next, depending on how the multi-processing, multi-threading happens in the background. And so I can see what's happening from a computational perspective, but also from a memory perspective, because as I load more data and I create new variables in my JupyterLab environment, this will increase the memory that's being used in this environment. And as I've said, we've got only 30 gigabytes worth of memory in this environment. And so if I go over the limit, there's a good chance that my JupyterLab environment will crash. So I need to keep an eye on this. And this kind of display tells me what's happening here. So I've got the memory here growing. You've got about 2.4 gigabytes here taken out of the 30 gigabytes. And we can see another a display of the memory usage in the right-hand side here, top right-hand side corner. And we need to keep an eye on this, not getting too high, too close to the 30 gigabyte limit. So as I said, the loading has taken about 2 minutes of time to load the data, Sentinel-2 data in my Python environment. And I've ended up with a data set of data object called data, surprisingly enough. And what I do here is I display this data set in the environment. Let me just click these. There we go. These annoying notifications. So displaying my data object here shows me this kind of display here, which I really like spending a bit of time on because it tells me a lot of things about my data set and how the data is organized. What's most important at this point in time is the fact that I've got 198 time slices within this 3-year period that I'm considering. So Sentinel data has been acquired over that period of time, and now I end up with a data array, a multidimensional matrix, if you like, with nearly 200 time slices. The size of my data set is about 600 by 600 pixels. It's again corresponds to the latitude and longitude extents that I've defined earlier. And I've got all these bands that I requested, the red, the green, the blue, the shortwave infrared band, as well as a band of quality assurance pixels, which we quality QA pixel QA information, which I will use later on to clean up the data set. And you can spend a bit more time trying to get further down to the way the data is organized. I won't go into too much detail at this point. This is a bit beyond the scope of this current session here. But this kind of display tells you what sort of data set you have to you are dealing with. So as I said, the first step typically after loading this data is to clean it up. So you have many pixels in these 200 time series, 200 time slices. Many of these pixels will be invalid as defined by maybe the satellite not having acquired data over specific regions and so on. And many pixels will be affected by pixel QA quality assurance issues. They might be masked by clouds, by shadows, they might be saturated and so on. So the first step that typically you have to apply to this data set is to clean it up. So remove all these data sets, remove all these corrupted pixels and come up with a time series of data that only contains the valid information. And so this is what I'm doing here over the next few code cells, which I'm executing now. And again, I won't go into too much detail about this data set here and how this the code here and how this is carried out. I've cleaned up all these bands that I've got, all these time slices. And the data set that I've got, I've interrogated the environment, and which is telling me that the data set size of this multidimensional multiband array is about 2.4 gigabytes. And again, this directly relates to the amount of memory that is being used in the Jupyter Lab environment. So I'm having another look at the one of the bands here. It all looks good. I get also information about how big each band is in memory. It's about 600 megabytes, for example. One other aspect that I'm doing or demonstrating in this notebook is to do a mask on the basis of a shapefile. So I've got this time series of images, if you like, acquired over this geographical region that I've defined, latitude, longitude, coordinates. But really all I'm interested in is the lake itself. So I want to grab the boundary of this lake and just remove from all the time slices, remove all the pixels that are outside this boundary. And so this is what I'm doing here. I'm loading up a shapefile, which I have pre-downloaded, if you like, or which I have available in my environment. I'm loading up this shapefile in the notebook. I inspect the different shapes in it, the CRS, the coordinate reference system. I have to reproject this data set and then extract the shape that corresponds to the lake. And this is a vector file, a resulting vector file of the shape of my lake. This is the region of interest that I want to filter. I want to filter out any pixel that is not within this shapefile, this shape. So this happens at the moment. I've got the vector, but I want to derive this, make this into a raster, which is what I'm doing in these code cells here. And I end up with a raster image, if you like, where each pixel is either true or false, is 1 or 0, determining whether the pixel is in the lake or outside the lake boundary. Subsequently, when I've derived this mask, I can simply apply it to the data, to this data object, using one single command, very, very straightforward. And I can then plot a few of the time slices. Remember, I've got almost 200 of them. I select 3 at random, so to speak, and just plot them in true color in this example here, just to have a bit of a feel for the data, have a look at the data, what sort of data it contains, and so on. So I can see that my lake has been extracted properly. So in each time slice, I've got the boundary of the lake clearly defined, and all the pixels outside the lake boundary have been filtered out. I can see that some of the clouds, well, all the clouds hopefully have been masked out, and all the pixels that were affected by QA issues have been masked out. So I'm pretty satisfied with this result. I can still see issues though, and that's one of the reasons to investigate at pretty much every step of the processing. I like to investigate, have a look at what the data set looks like, because we can see that some of the areas of shadows in various parts of the time series, they have not been filtered out properly. So I've got this step earlier saying, remove all the shadows pixels and remove all the cloud affected pixels and so on. But clearly this process is not very accurate. So there are still leftover regions in my data set that contain further issues in the data set. So it's beyond the scope of this particular notebook to try and find ways to remove these pixels further, to mitigate these effects further. But this is something I'll have to keep in mind for later processing in this notebook. Another filtering that I can do is to look at the data and to try and remove all the pixels that are not water, because ultimately I want to calculate TSS concentration in lake waters. If a pixel has got vegetation or floating debris or is just dry because it's a drought or a dry period at a time, I want to remove that pixel as well. I don't want to apply the algorithm for TSS measurements earlier. I don't want to apply it to that pixel, which is not water. So one way to do this is to derive an index, the so-called normalized difference water index, which also works on the basis of the bands in this data set, so the remote sensing bands, and which gives me a bit of an overview of which pixel is likely to be water and which pixel is likely to be non-water. And then on the basis of this, I can further filter out my data set. I did not come up with this index myself. I grabbed that from the literature as well, from the existing work on water research in water bodies and so on. So I'm creating a new band in my data set as per this formula here, this equation, which is reproduced in this bit of code here, and I create a new normalized water index band in my data set. So I can then look at this new band, this water index, as done here in this plot. So I'm using a few more time slices to have a look at. But again, the 12 time slices picked at random through the time series. But that shows me that for some of the time slices, I get some good results in that some of the index results, water index results, tell me that some of the regions on the lake are clearly water. They're index values above 0, so in shades of red. And some of the pixels around the edges of the lake are deemed to be non-water because the index is below 0. So this seems to be working relatively well. And I can then use this index, which again, I've derived for every single time slice in the time series. I can apply this now to the whole data set and filter these values, these non-water pixels out. So again, I plot some of the results once this filtering operation has been carried out. For these 3 time slices, it doesn't look like this made much of a difference, but it may do so for other time slices. The next section in this notebook, there's the TSS, the suspended sediment calculation, as per the algorithm that I mentioned earlier. So you will perhaps remember or recognize some of these variables and values from the earlier algorithm that I implemented here. And this is simply calculating this TSS index for that time series. And so I have now created a new TSS data set, which I'm displaying here again. And I can display some of these results for the current time series, which is what will be done here. So this is kind of a first look at the TSS time series. So once I have taken all these bands from the Sentinel time series, from the Sentinel sensor, and I've used them as per the algorithm that I described earlier in the notebook, and I apply them to every single time slice in the time series, I now have the results for, again, 12 selected time slices across the time series. So we can see that different times have got different results. Some of the time slices have got elevated levels of TSS, whereas some other time slices have got lower levels, and so on. We can see the effect of cloud shadows, the residual effect of cloud shadows. Again, as I mentioned earlier, some of these residual effects are still in the data set. So we should really go back to the original time series and try as much as we can to clean it up further, to remove and to avoid these artifacts here, which will, to a certain extent, bias the results later on. Now, the next bit of the next few sections in this notebook is about doing some kind of temporal averaging and temporal operations. You can have a look at these first results for each time series, but you have 200 time series to look at, and most of them will be affected by clouds and shadows, and lots of these pixels will be missing. So it doesn't lead to a very insightful representation of the data. So one thing you can do is to do a temporal aggregation, and there's different ways of doing this kind of averaging process. The first one I'm demonstrating here is to say, instead of looking at each time slice separately, you grab a collection of time slices, for example, for a week or for a month, and you average those. And then you have an average over this period of time, which will hopefully provide a bit of a better insight into your data set. What I'm demonstrating here with this next series of code is doing the averaging of the quarters. So using 3 months in the year, and each 3 months, I'm doing an average as per what I just described. So this happens here. Again, looking at the data set, but more importantly, plotting some results on screen. So over 3 years, I end up with 12 quarters. I'm plotting, again, a selection of 9 quarters, quarterly averages, if you like, of TSS. in this plot here, just for demonstration purposes. So you can see how things start to evolve through time. You can start to understand the dynamics of TSS through time, quarter by quarter. And what you will see is that most pixels in these representations is available because we have made an average of a longer period of time, which means that missing pixels in specific time series, that time slices, do not end up to a missing pixel in the final average. If that pixel through time has a few missing values, it will still be able to produce averages. So it gives a bit of a more complete sort of view of the resulting data set. Now, another way of doing the aggregation is to, instead of taking a quarter by quarter or month by month and aggregate over this, is to say, let's look at all the time slices over the 3-year time series. I grab all the time slices that fall in the June month, and I do an average over these. Then I do the same for February month. So all the time slices over the time, the selected time period, all the time slices that fall within January. And I take all the January time slices and do an average over this. So this is a different way of looking at the data. I'm again doing the calculations here. This is fairly straightforward. You can execute fairly quickly. And this time I'm plotting all the resulting months over the selected 3 years worth of data to get a bit of an idea of the TSS levels at different times of the year. So what this kind of result tells me is that in January, February, March, there's typically, on average, consistently higher levels of TSS compared to May, June, and July, for example. So you can, again, start to understand the dynamics. This is within a year, understand the dynamics of what TSS levels are doing in the lake and potentially come up with conclusions or remedial actions if you need be, and so on. Now, a third way of doing averaging, I guess, is doing a temporal average for the whole time period. So looking at the whole 3 years worth of data and doing a grand average over this entire period. So this is an example here for this TSS time series. Now, the trouble with this kind of a standard approach, it's very easy to do from a coding perspective. All you do is you take your data object and you apply the dot mean function, and it spits out your grand average over the whole time period. Remember, however, that several pixels along this time series will be corrupt, and therefore they might have very low values because it's in an area of cloud shadows, for example, or there might be an erroneous pixel, a saturated pixel that hasn't been cleaned up, and therefore it's high value of TSS. So these values, low or high, will typically lead to biases in your resulting averaging operation. So one way to do this, and this is something I demonstrate in this notebook, I don't want to go into too much detail here, but is to apply robust functions in which you look at the time series at a given pixel and you remove the outliers first before applying the averaging function. And therefore it kind of mitigates these issues of residual corrupt pixels in your time series to a certain extent, and hopefully leads to a more robust average of your time series. So this is done here by defining a couple of functions, custom functions, which I then apply to the data set using the apply ufunc function. Again, I won't go into the detail of this. Another way of doing it is using the map blocks directive, which you can do as well. But this is something that allows me to apply my custom averaging function to the data set, to this multi-dimensional array of data. And we can see again on the right-hand side that this is typically applied in a parallelized fashion to the data set. We can see this again by applying the second custom function to the data set, which is a coefficient of variation calculation. So the data is being calculated. We can see that the star has appeared here in the cell, but soon will turn to a number when it's finished calculating. And again, keep an eye on the memory requirements. We can see that in this notebook, the memory keeps creeping up because I make no efforts to try and get rid of variables that I don't need. So if you start hitting, if it start getting red here, memory, you know that you're in a bit of trouble. So that's potentially something to keep in mind if your data set is very big. Now I'm doing the plots, the resulting plots, including on the left-hand side, the robust mean of the whole time series. So there isn't too much difference compared to the earlier data set, the earlier average results, which I presented before. But at least here we know that the result has been applied, has used a robust approach to calculating the mean. On the right-hand side, I have the so-called coefficient of variation, the CV, of the whole of the same time series, and it gives me an indication of the relative variability of each of the pixels. So if we have a very low value, it has very small variability from in a relative sense, as opposed to a red pixel, a reddish pixel, which has a much higher variability over that time series. And so you can start looking at the results and maybe pinpointing some areas of hotspots, TSS hotspots, maybe when rivers are periodically releasing TSS into the lake. They, after rainfall events, they get a big load of TSS, of suspended solids, into the lake, and then goes back down again until the next rainfall event. So you might go up and down. So it gives a much higher variability in these regions. So you might want to go down and have a look what's happening on the ground, or again, maybe look at which sort of rivers are flowing into the lake at these points, etc. Finally, a last demonstration that I'm doing in this notebook here is to look at time series extraction of pixel values, which we also called pixel drills, from the time series, which is something that people typically want to look at, are interested in doing. So in this example, I'm selecting 5 points, more or less at random as well, along a transect across the lake. And I just want to extract the values of TSS through time for these 5 points here, as highlighted here. And so this is done again fairly simply, using very simple operations in Python. And then I can simply very easily plot the resulting time series at these 5 points with different lines, different colors. What I'm using, the data set I'm using to extract the values here is the data set of quarterly averaged TSS values. And therefore we have only 1 point per quarter along this time series. And so we can start seeing different dynamics happening at different times of this time series, 3-year time series, with elevated TSS levels for most of it, and fairly low levels for whatever reason in that quarter here. Again, maybe that tells you something about what happened in the lake at that particular time in this particular quarter. You might want to go back to the data set to try and work out what happened and why we had such low values at that point, etc. Finally, once you have your time series, you can also extract this into a pandas, so-called pandas data frame object. As you can see here, this is basically a tabular representation of the time series that I just extracted. And you can also, I think I just reformat this in a different format that maybe is more suitable to what you want to use. So you have for a year column, a month, we have 4 different months, if you like. Should be quarter. We should have renamed this into quarter, for example. And for each of these, you have 5 different points for which you have a TSS value. And finally, you can use this bit of code here to save it to file. which I've just done by executing this this command here, and which has created a data set, an Excel spreadsheet data set, CSV file, if you like, of data, which I can then open to have a look at, and we can see my data time series here for each year, for each month, and each point, which I can then use to as an input to my other analyses or to pass on to someone else for further processing. So this is the end of this particular notebook. There was a lot going on probably for you. Feel free to come back to it at a later stage if you want to get more information. I'm happy to take questions. I see there's been a bit of activity on the chat, which I haven't had a look at yet. So we can definitely take questions now. And hopefully that's given you a bit of a feel for the sort of operations that you can do with the kind of data sets that are available on the EASI platform. And again, the rest of the team here, the Hackathon team, are here to help you out, to answer your questions, and to help guide you through these various processes as a function of how you want to how you want to implement and what you want to implement, what sort of ideas you have to implement in your project. So I might pass on back to maybe Roshni or to whoever is around, and I'll spend a bit of time looking at what's happened in the chat in the meantime.
Great, thank you very much, Eric. I guess we'll open up to questions now. If anybody would have any questions, please feel free to unmute and ask them or put them into the chat. And Eric, Caitlin, and other members of our team will be very happy to answer and support you.
Eric, there was a question in the chat that I couldn't answer just about for TSS. Was there preliminary field survey for presence and absence? Perhaps you could talk a little bit about that. Yep.
Yeah, thanks, Caitlin. I'm just reading the question now. Field survey, presence, absence of sediments. So do we really work on that? So I did not personally do any work on the derivation of this algorithm here. So all I did was to look at this publication here, in which the authors do this kind of work. So they did go and grab and measure, took samples of water in the lake on the same day that the satellite went overhead and took a picture of the lake, and then they did the correlation. So they fitted this algorithm here on the basis of the measurements they took at the time in the lake waters. So exactly how they derived how they fitted this algorithm, I'm not quite sure. This is probably well explained. I can't remember now off the top of my head how they explain it in this paper, but I did not do any research in terms of whether the TSS was present or absent in the time series and so on. All I've done is to take this set of formulas, this set of equations, and I've applied this to the time series of remote sensing data available on EASI. So some of I'm reading the question. I have to read the question again, I think. But some of the time slices will definitely have a high level of TSS, but some others will have lower values of TSS. So we're looking where contribution outputs. Yeah, I'm not quite sure about the question exactly, to be honest. So maybe Bam, if you want to unmute or if you want to ask for the question, please feel free to unmute and have a bit of a chat.
Yeah, thanks, Eric. I was just curious whether this is kind of unsupervised classification or we got some data from the field, then we trained the computer on that. So I'm satisfied, and I will have a look at those papers. I think it will also give additional ideas. Thanks.
No problem. Yeah, thanks for clarifying, Bam. And definitely, yeah. So this is a totally supervised approach where you fit your method first, you fit your algorithm on the basis of ground truth data, and then you just apply it. You extrapolate, if you like, and you predict over a further region of interest. So yeah, no real learning or online learning at this point.
Thank you.
I think it's kind of relevant to talk about, given there was also sort of a question about machine learning as well. It's definitely something you can do in these environments because they're based in Python. You can bring in standard Python machine learning packages, particularly scikit-learn is something we use a lot. And so really you would need to bring data to that or create training data, or you could do an unsupervised classification. So we do have a good example in Africa that I've put in the chat. So if your idea for this week does include machine learning and it's something you'd like to look at, it might be something we can help you start this week or talk about, or even you can mention it in your presentation at the end of the week. And if you went on to the launch phase of the program, we could then provide some additional support in helping you, source relevant data, or, once you've collected data from the field to use for a supervised classification, we could provide sort of technical support to, share a lot of the learnings we've had along the way in working in Australia and Africa on these sort of projects. So in particular, we're looking at sort of crop detection and classification and things like that. So there's a question about supporting PyTorch and whether GPUs are available. Eric or Matt, do you want to cover that?
Yeah, good question. Matt will be able to address this probably more than I do. I haven't used PyTorch. I would hazard a guess that it's feasible to use it on EASI. I'm just not sure about the GPU aspect. Matt, if you want to unmute and have a chat, you're muted.
Yeah. PyTorch and machine learning libraries will be available. It's TensorFlow as well, and some of the scikit packages. So they're available as Python libraries. GPUs are possible within the EASI family. I don't think I've got them enabled presently for Asia, but find the right use case and be willing to go on the learning journey with us. No problem. We should be able to do that. Thanks.
Thanks, Matt. And there was just a question as well about memory requirements, and I just want to quickly touch on that too. The question was about the fact that it's using 12 gigabyte of 28, and as I said, I made no effort trying to optimize the memory requirements. The reason being that I know there's 30 gigabyte available, and after running the notebook once, I know that my notebook fits within the requirements of these 30 gigabytes. So I could have started deleting variables that I didn't use anymore. You would free up space that way. But I didn't feel the need to do that because I knew that my notebook was small enough, so to speak, so that it will fit within this 30 gigabyte limit. If your data set is getting bigger and you want to extend the spatial range or the temporal range of your data set quickly, you will hit that 30 gigabyte limit very quickly, and your notebook is going to crash. So you will know when that happens. But then you can move on to further, start making use of different further tools, including the use of Dask and a cluster of Dask nodes, which allows you to have potentially terabytes worth of RAM in which you can load up your data, load up a data set that's much bigger than the memory of your Jupyter Lab environment. So it will be orders of magnitudes larger than 30 gigabyte. So you can load up really large data set in this cluster of Dask nodes in a distributed fashion, process it again in a distributed fashion. You have all these nodes that do the computation for you, so to speak. in a parallelized fashion, and then bring the resulting results, which hopefully fit inside the 30 gigabyte limit, back into your notebook. And even if you can't do this, you have ways to visualize the really large volumes of results, or large volumes of data that is located on your DAS cluster, but have it visually appear in your notebook, even if you have only 30 gigabytes worth of data. So there's potential for processing much further data sets, much bigger volume of data on these kind of cloud-based platforms.
Okay, thank you so much.
No problem.
I thought I'd just mention again that working through these things, you know, it can be challenging, and you may run into frustrations when you're using the environment. If you are, that's why we're here. We're here to support you through those. So if you try something and it's not working and you're not sure why, that's why we've set up a huge number of these technical drop-in sessions. So I'm just going to add the link in the chat, but it's also available in your participants handbook. And the idea is that if you're having trouble, there's many 20-minute time slots over the next 3 days where I'll be around, or Eric or Matt or some of our other experts, and you can come and ask us a question. And if we don't know, we will find someone who does know. And that may help with, you know, enabling you to prototype your ideas quickly during this week and explore during this week. We're not expecting you to come up with a final product run over a huge area. This whole week is very much about coming up with new ideas and testing them out in this environment. And so I definitely encourage you to be ambitious, but if you're having technical challenges, that's what we're here for. And I think my advice is, you know, keep your sort of areas that you want to look at small to begin with until you have finished sort of prototyping everything you want to look at. And then you can come and talk to us about how to sort of make it run better, faster, over more area. But really, you know, this time is for you to play and see what works. And it's a learning experience. So if you're new to coding, that's okay. This is about, you know, showing up, trying your best, getting some help, and, you know, exploring this new sort of method of interacting with Earth observation data. So yeah, with that, I'll might hand back to Roshni.